To Talk 11, the final talk in our extended series on interpreting veterinary literature. Today we're covering linear regression and ANOVA, the workhorses of continuous outcome analysis. These appear whenever the outcome of interest is a measured number. Creatinine concentration, body weight, blood pressure, pain scale score, intraocular pressure, or any other quantitative measurement. If you've made it through the previous talks, you'll find this one builds naturally on what you already know. The core logic, coefficients, confidence intervals, p-values, multivariable adjustment is the same as logistic and Cox regression. The difference is the output. Instead of odds ratios or hazard ratios, you get beta coefficients in the original units of measurements. Let's get into it. Roadmap: linear regression for continuous outcomes, ANOVA for multi-group comparisons. We'll spend time on both the interpretation of outputs and the key assumptions, because violating those assumptions silently is a common source of misleading results. The unifying concept throughout is the same one from all our previous regression talks. What is the independent association of each variable with the outcome after accounting for everything else? The right regression model is step one in evaluating any paper's methods section. The outcome variable determines the model. Continuous outcome, linear regression. Binary outcome, logistic regression. Time to event, Cox regression. These aren't interchangeable. A common error is applying linear regression to pain scores or other bounded scales. Technically, these are ordinal, not truly continuous, and if the distribution is skewed or bounded, linear regression assumptions may be violated. Ordinal logistic regression or non-parametric alternatives may be more appropriate. When you see linear regression applied to a pain score, check whether the residual distribution looks normal. In practice, the clearest cases for linear regression are physiological measurements, serum chemistry values, blood pressure, body weight, echocardiographic dimensions, things that genuinely exist on a continuous numeric scale. Here's the beauty of linear regression compared to logistic regression. The output is directly clinically interpretable without any back transformation. The beta coefficient is in the same units as your outcome. If you're modeling serum creatinine in micromoles per liter, a beta of plus 4.2 for age means for each additional year of age, creatinine is predicted to be 4.2 micromoles per liter higher after adjusting for all other variables in the model. The intercept, beta naught, is the predicted outcome value when all predictors equal 0. It often doesn't have a meaningful clinical interpretation on its own, but it anchors the regression line. The confidence interval for each beta coefficient is the range of plausible values for that association. If the CI crosses 0, no effect. The predictor is not statistically significant. This is directly analogous to the CI crossing 1 for odds ratios and hazard ratios. R-squared is the model level summary statistic for linear regression. It tells you how much of the variation in the outcome is captured by your set of predictors together. An R-squared of 0.68 for a creatinine model means knowing age, blood pressure, phosphorus, weight, and sex explains 68% of the variation in creatinine between cats. That's reasonably good for biological data, where many unmeasured factors always contribute. But R-squared can be misleading. Adding more predictors to a model always increases R-squared, even if those predictors are useless. Just by chance, they account for a tiny bit of variance. Adjusted R-squared corrects for this by penalizing the addition of non-informative predictors. And critically, a high R-squared doesn't mean every individual predictor matters. You could have R-squared equals 0.75 with only 2 significant predictors and 3 non-significant ones. Always evaluate each predictor's beta and CI individually. The residual plot is to linear regression what the Bland-Altman plot is to method comparison. It's the diagnostic check that tells you whether the model is appropriate. Residuals are the differences between each observed outcome and the model's predicted value. If the model fits well, residuals should be randomly scattered around 0 with no patterns across the full range of fitted values. If you see a fan shape where the spread of residuals increases as fitted values get larger, you have heteroscedasticity. The model's predictions are less reliable at higher values. This can often be fixed with a log transformation of the outcome. A curved pattern means the relationship between predictor and outcome isn't linear. A more complex model is needed. Transformation, splines, or polynomial terms may be required. When you read a linear regression paper and there's no residual plot and no mention of assumption checking, that's a yellow flag. Ask, how do we know the model was appropriate? The multiple linear regression table is read exactly like the logistic and Cox regression tables from talks 5 and 9, row by row, checking direction, magnitude, and confidence interval for each predictor. The key difference is that the coefficients are in original units, making them directly interpretable without transformation. A beta of plus 18.5 for phosphorus means that each 1 micromole per liter increase in serum phosphorus is independently associated with 18.5 micromoles per liter higher creatinine. That's a large, clinically significant association. Watch for overfitting. The same rule of thumb applies as for logistic regression. You need sufficient observations per predictor. For linear regression, a rough guideline is at least 10 to 20 subjects per predictor in the model, though the more rigorous requirement is based on the residual variance structure. ANOVA is the extension of the t-test to 3 or more groups. It answers one question. Are all these group means the same, or do at least some differ? The F statistic is a ratio. Large F means the variation between groups is large relative to variation within groups, suggesting real group differences. A significant p-value tells you the groups are not all equal, but it doesn't tell you which groups differ from which. That's where post-hoc tests come in. Tukey's honestly significant difference is the most common. It performs all pairwise comparisons while controlling the family-wise error rate. Bonferroni correction is more conservative. Dunnett's test is used when you're comparing multiple groups to a single control. The critical habit. When you see ANOVA in a paper, always look for the post-hoc comparisons. A p-value of 0.001 from ANOVA is not actionable on its own. You need to know which specific groups are different and by how much. Let's work through both parts of this case question together. First, which predictors are independently significant? Age? Yes. Confidence interval plus 2.8 to plus 5.6. Doesn't cross 0. Phosphorus? Yes. Confidence interval plus 9.2 to plus 27.8. Large effect? Doesn't cross 0. Body weight? Yes. Confidence interval minus 10.1 to negative 2.5. doesn't cross 0. Sex, no. Confidence interval for sex is negative 11.4 to plus 5.2. It crosses 0. Not statistically significant after adjusting for the other variables. Part 2, prediction. We don't have the intercept from the case, so let's reason qualitatively. A 12-year-old cat, 12 times 4.2 equals plus 50.4 contribution from age. Phosphorus of 2.8 micromoles per liter, 2.8 times 18.5 equals plus 51.8 from phosphorus. Body weight, 4 kilograms. 4 times negative 6.3 equals negative 25.2 from weight. Before the intercept, the combined contribution of these three factors sums to a substantial positive creatinine value. This cat is expected to have meaningfully elevated creatinine. What does R squared equals 0.68 tell you about the prediction? It means the model accounts for 68% of creatinine variability. For an individual cat, the remaining 32% from unmeasured factors, biological noise, measurement, and precision, contributes real uncertainty to the prediction. Model level R squared doesn't translate directly to individual prediction accuracy. Use prediction intervals, not confidence intervals, for individual patient predictions. Key lesson. The beta coefficient gives you the average relationship. Individual predictions are always less certain than the model level statistics suggest. We've completed the full extended series, 11 talks covering the entire landscape of veterinary clinical literature interpretation. Let me give you the master summary. Choose your model based on your outcome type. Read beta coefficients and CIs in original units for linear regression. Check residual plots. For ANOVA, the F-test is just the beginning. Post-hoc comparisons tell you what matters clinically. And across every single talk in this series, the same three questions apply. What is the effect size? How confident are we? Is it clinically meaningful, not just statistically significant? Those three questions, applied consistently, will make you a much more effective reader of veterinary literature than memorizing any specific test or formula. Thank you for being part of this series. If you'd like more short, clear epidemiology lessons, feel free to subscribe so you don't miss new videos. And if these explanations help make the concepts click, a quick like on the videos tells YouTube to share them with other students who might need help. Thanks for joining, and see you next time.